Okay, so now we're in section 3.9. It's still one of the sections from the OpenStax 1, and it's derivatives of exponential and log functions.
Sign-in verification system. Please press the pound key to finish your verification.
And so the learning objectives, I do them in a different order. I actually do derivative of logarithms first, then exponents, and then I also show you how to do logarithmic differentiation. So I actually do these, the second goal, the third goal, and then the first goal. So that's the order I tend to do them in. I like it better. Okay, so the first function I want to talk about is the natural logarithm function. And it is defined as the function, the natural log of x is the integral from 1 to x of 1 over t dt. So what is an integral? Well, when you take an integral, it's actually the area under the curve of a particular function. So if I look at this function 1 over x, and I draw it, don't need that much. Okay, so here is the function 1 over x, and it decreases rather rapidly. I'm going, what happened? Oh, I have no idea what just happened. Oh, why am I in the master? How did I get there? Okay, I'm back. Okay, so this is the function 1 over x. And the logarithm function is defined to be the area under the curve of this function from any value of 1 to x. So here, if I draw this function like this is y is equal to the natural log of x. Here is y is equal to 1 over x. Okay, so it goes through the point 1, 0. All right, so the point 1, 0 is on the curve. So since the point 1, 0 is on the curve, that means that the natural log of 1 is 0. So we know that now, we have that information. And so this is, if I take and I start at 1, which would be right here, and I find a value of x, let's say x is right here, then by definition, it is the area under the curve up to the value of x. So that's what this log value is. So this function, this value right here for x, which is the natural log of whatever that x is specifically by definition the area under the curve of the function 1 over x up to the value of x, 1 over t up to the value of x. Now, it's easy to find certain things. Like I said, the natural log of 1 is easy because you get the integral from 1 to 1, and the integral from 1 to 1, well, there's no area there, so that's 0. Calculators can help you find things. For example, I love this. OneNote does it for you. So the natural log of 2 is equal to, there it is, 0.69, whatever. Notice that if I try to take the natural log of a number that is between 0 and 1, so let's say I choose this value of x over here, notice that the area under the curve is going to be negative. So I would get this area. So I'm going to get a negative area. So therefore, one of the things that we can say is that if x is between 0 and 1, then the natural log of that number will be negative. The other thing that's very important to know is we can't take the natural log of 0. It does not exist. Neither does the natural log of any negative number. So that's how we find what the actual function is. So we can define the function simply to be y equal to the natural log of x, and you now know what it looks like. So it looks like this red curve. So that is y is equal to the natural log of x. Okay, now that we have an idea of what the natural log looks like, what we'd like to be able to do is, once we know how a function is manipulated, we want to be able to take its derivative. Okay, so now here's where we define the natural logarithm. And now we want to take the derivative of this function. And in order to take the derivative, we need to utilize the fundamental theorem of calculus. All right, so now here's the fundamental theorem of calculus. I know I'm dusting off some brains here because it's something that you learned at the very end of Calculus 1. And the fundamental theorem of calculus says, if I take the derivative of an integral, they're almost inverse functions of each other. If I integrate something, I'm going to get its antiderivative. When I take its derivative, I'm going to get the function back. That's the fundamental theorem of calculus. So if you take the integral from a to x and then differentiate that f of t, you just get f. So just for an example, you might remember something like this. Let's say we have the integral, the derivative with respect to x of the integral from 2 to x of the cosine cubed of t dt. Now, we don't know how to integrate cosine cubed yet. You will know by the end of the course. You'll know by 2/3 of the way through, you'll know how to integrate cosine cubed. But right now, we don't know how to integrate cosine cubed, but we don't have to, because the fundamental theorem of calculus says we're just going to take that cosine and evaluate it at x. And that's what we get. So the fundamental theorem of calculus says, in order to find the derivative of an integral of a function evaluated at t, it's just the function evaluated at x. All righty, so let's use that to find the derivative of the log. Well, we said from before that the log function is the integral from 1 to x of 1 over t. So this right here inside is my log function. So when I go to take the derivative of the log, I'm just going to stick this in as what I define to be the log function. But by the fundamental theorem of calculus, the derivative of the integral of a function of t is just that function of x. And so very nicely, we now know that the derivative, so if y is the natural log of x, then the derivative of y with respect to x is 1 over x. So that's the derivative of the log function. Nice and simple, commit it to memory. You will need it in several problems. Okay, that's the derivative of the log function. We are going to be integrating and doing all kinds of things, but that's what we have for the derivative of the log function. Okay. All righty. So let's now suppose that we don't just have the log of x, we have the log of a function of x. So now if you remember from when we did the inverse tangent functions, and we had the inverse tangent of something, or the inverse cosine of something, or as we say, arctangent, and we took its derivative. If we had a function of x, we had to multiply by derivative. That was the chain rule. So we're going to do the same thing here, okay? So given y now, you're given that y is equal to the natural log of u, and u is some function of x. Then in order to find the derivative with respect to x of y, we need the derivative of y with respect to u. times du dx. Okay. The derivative of y with respect to u, that says take the derivative of that. Well, that's just going to be 1 over u. All right, because it's a function of u, I'm taking the derivative with the variable u. So I'm just going to get 1 over u. And then I multiply by whatever derivative I had, which was du dx. So therefore, now you know how to use define the derivative of the log of a function. So if y is the log of u of x, then dy dx is 1 over u of x times du dx. Okay. So it's always helpful if we have some examples, otherwise we can't make this thing concrete. So I'm going to pull up my examples right here. So for these examples, we want to find dy dx. Now the first one's easy because it's just x. It's no function of x, it's just x. Okay, so in number 1, y is equal to the log of x. And so therefore its derivative dy dx, we know, says take that x, throw it in the denominator, and we're done. Don't need to do anything else. I'm done.
President,
Okay, yes.
could you scroll up just a tad bit, please?
Hi, Diara.
And hi, Professor.
How are you?
I'm good, and yourself?
I'm good.
That's good.
Much, much better now.
All right, you're good.
Okay. All righty. So the derivative of that first one was easy, and this one we know by definition. That's the way it was defined. Commit that to memory. What's the derivative of log of x? 1 over x. Bam, we are there. Okay, now 2 is going to be a little different. I now have the log of 5x. So here you can see that y is the natural log of u, where u is 5x. So dy du is 1 over u, and du dx, oh, I don't want a times there. I just want a space. And du dx is 5. Okay, so using the chain rule, dy dx is going to be 1 over u, but u is 5x. And then I'm going to multiply by its derivative, which is 5, and I get 1 over x. Oh, that was pretty nice. I like that. That worked really well. Okay. Number 3. So number 3 says y is equal to the natural log of 7x cubed minus 2x. So y is equal to the natural log of 7x cubed minus 2x. So again, y is equal to the natural log of u. Here's my u. and u is equal to 7x cubed minus 2. So dy du is always just 1 over u. That's what this derivative is for the logarithm. And du dx, nice and easy. 21, I think I forgot an x. 21x squared minus 2. So dy dx that's going to equal 1 over u. So here's u, 7x cubed minus 2x, so that's 1 over u. And then its derivative goes right in the top, which is 21x squared minus 2. So this is 21x squared minus 2 divided by 7x cubed minus 2x. And guess who's going to do number 4? You are. Y is equal to the log of cosine x. And I am going to take roll. Anybody have an answer for me? You were supposed to be working on this problem. Y is
Would it
equal.
be
Go ahead.
negative tangent?
Negative tangent of x. That's correct. Anybody get something different? Anybody need help? All right. So here, y is equal to the natural log of u. U is the cosine of x. Uh-oh, move my mouse. Stop. U is equal to the cosine of x. So dy du is 1 over u, and du dx is equal to negative sine of x. Okay, so dy dx is dy du, which puts u in the denominator. Du dx is negative sine x, so that's in the numerator. So I get negative tangent x. Okay, any questions? All right, we have one last one, and that is the log of the square root of x squared plus 1. Okay. All right, so if y is equal to the log of the square root of x squared plus 1, I think I might like to write that better. Dawn, personally, I don't like taking derivatives of square roots. I like taking derivatives of functions with powers. So I'm going to rewrite this as this is the natural log of x squared plus 1 to the 1/2 power. Okay. So therefore, I'm going to get y is equal to the natural log of u, where u is equal to x squared plus 1 to the 1/2 power. So I get dy du is a logarithm. 1 over u doesn't change. Du dx. Okay, who wants to give me du dx? Chain rule. We've been working and practicing our chain rule. How do we do du dx?
It'd be 1/2 x squared plus 1 times 2x.
Okay, but you forgot my power.
Oh,
That'd be 3/2.
oh, that's negative half.
Negative 1/2. Good. We subtract 1. Okay, so we subtract 1 from the 1/2, which gives us negative 1/2, and then we have to multiply it by the derivative of 2 of x squared, which gives us 2x. Okay, so let's put it together. So dy dx is equal to 1 over u, but u is x squared plus 1 to the 1/2 power. And then I'm going to multiply, well, the 1/2 and the 2 are going to divide out. So I'm going to get x times x squared plus 1 to the negative 1/2 power. And when I simplify that, I can get that x squared plus 1 to fly down into the denominator because of its negative exponent. And so then that's going to give me x squared plus 1, and that's it. Okay, any questions? All righty. Give you a minute to take a peek at that before we move on.
Could you scroll up a little bit, Professor, please?
I certainly can.
Hello. Hello.
Yes.
Oh, so that negative 1/2 it canceled out with the other half.
Well, actually, it added to it. So it put the x squared plus 1 to the positive 1/2 in the denominator. So then you have x squared plus 1 to the 1/2 times x squared plus 1 to the 1/2. You add the exponents. So 1/2 plus 1/2 gives you 1. Doesn't cancel, it adds to it. Okay, Diara, am I good to move up?
Yes, you're good.
Okay. All righty. So let's talk about some properties of logarithms, because the properties of logarithms can make some of these problems so much easier if we just use the properties. I tell you, use the properties, then you won't be so frustrated. Okay, so the first property is going to be, well, why am I eraser? Come on down. Yep, do what you're supposed to do. All right, so the first property is the product rule. Okay, so we want to, product rule says if I take the log of A times B, that's just the log of A times the log of B. And that makes life really simple when we go to do these problems. So the first thing we're going to do is we're going to find dy dx, but we're going to use the product rule to simplify first. Okay, So using the product rule is going to help us simplify finding the derivatives of these. All right, so we're going to start off with number 1. We know y is equal to the natural log of 5x cubed minus 4 times 3x minus 4. Now, the way what we want to do is we want to simplify this so that we can take the derivative of it. So in order to simplify this,
Go up just a little bit.
go up a little bit
Yeah, just a little. Yeah.
there.
Yeah.
Okay. So we're going to use the product rule. So the product rule says, let's simplify this by making this the log of 5x cubed minus 4 plus the log of 3x minus 4. So now that I simplified it, it's much easier to take a derivative because now I don't have to take the derivative using the product rule. So now I can do dy dx. For the first term,
Wait, are they added together or are they multiplied
they
together?
are multiplied together, but the rule, oh geez, that should have a plus in the middle. There's a plus missing. Thank you. There's a plus missing, you know. Interesting when I find mistakes in my second section and the first section didn't find it at all. They didn't even see it. I guess I'll have to go back with them because they sure missed that. Okay, yes, you got it. There is a plus. A plus, you got it. Okay. All right, so now dy dx, I can, for the first one, the derivative is going to put 5x cubed minus 4 in the denominator. And it's going to put 15x squared in the numerator. And then the second one is going to put 3x minus 4 in the denominator. And then it's going to put 3 in the numerator. And that's it. I am done. Okay. For number 2, I have y is equal to the natural log of the cosine of x times the tangent squared of x. Okay, so simplify, I'm going to get y is equal to the natural log of the cosine of x plus the natural log, and this is the tangent of x quantity squared. So therefore, I get the derivative of y with respect to x. I'm going to put that cosine in the denominator. Bam, there it is. We already did this one. And take its derivative, so I get negative sine x in the numerator. And here, I'm going to put tangent squared in the denominator. And then I need to multiply by its derivative. Well, its derivative, I have to use the chain rule. So the derivative with respect to x of the tangent squared of x, you're going to bring the 2 down and get the tangent of x. Then you got to multiply by its derivative, which is secant squared x. So this becomes 2 tangent x secant squared x. And so now I have a final answer. I can't believe nobody from that first section, all that math I did not get that formula, was incorrect. Okay, so now I get dy dx is equal to negative tangent x plus 2 times the secant squared of x over the tangent of x. And I'm done. Okay, any questions? All right, so that's how we use our product rule. Our product rule is very important to us, all right, because it simplifies things where we're taking the log of a product. But equally as important is the quotient rule. Very much like the product rule, except with the quotient, the log of A divided by B becomes the log of A minus the log of B. Okay. So again, we want to solve this problem. We want to find dy dx, but we want to use the quotient rule to simplify first. Okay. So I'm going to start out with the log of y. No, I'm sorry. I'm starting out with y is equal to the natural log of 3x squared minus 5 divided by 2 plus sine x. So now I'm going to split that up and write that as the log of 3x squared minus 5 minus the log of 2 plus sine x. And what I want you to do is find dy dx and then let me know what it is. Okay. Looking for an answer. Hello. I'm looking for an answer. Do you not know what to do?
Can I go through the steps real quick?
Say that again.
Would we be able to go over like the steps real quick?
Okay. All right, so remember, once it looks like this, then I can just take the derivative of each piece. So maybe you guys needed to see it down here first. Maybe you needed to see that y is the natural log of 3x squared minus 5 minus the natural log of 2 plus sine x.
Professor,
Yes.
natural log of 3x squared minus 5. Wouldn't it be, if I did it right, 6x over 3x squared minus 5?
Okay. So we're
And
going to 6x squared over,
3x squared minus 5.
that's right,
And then you subtract that by cosine over 2 plus sine x.
over 2 plus sine x. Thank you very much. Okay, anybody who, I can't remember, see her, whose voice that was that wanted to go through the steps. Is that okay now?
Yeah, that's good.
All right. Okay, last rule. So this last rule is the power rule. And, oh, I forgot, I wanted to put a problem in, a nice simple problem in here, but it wouldn't do it for me. Let me try it. Y is equal to okay, yeah, that's what happened before. It wouldn't let me keep my numbers. That's fine. I got rid of the numbers and wrote them in myself. Okay, this is 1, 2, 3.
I got a question.
Yes.
For the derivative of the 3x squared minus 5, wouldn't it just be 6?
Oh, it's just 6x. She said 6x and I wrote 6x squared. You are correct. Yeah. She did say it correctly. I wrote it wrong. Okay. All right, so the last is the power rule. All right, so with the power rule, it says that when you take the log of x to a power, then you can move that n down in front and make it n log of x. It also works this way. If you have the log of u of x to a power, you can bring that n down and get the natural log of u of x. So that also works as well. Okay, so that's the power rule. Okay, so the first one, again, we're going to differentiate these, but we're going to use the power rule to help simplify. Okay, so we're going to find dy dx. But we're going to use the power rule. To simplify. First. Okay. All right, so in number 1, I have y is equal to the log of x to the 6th power. So the simplification that we're going to do we're going to make this y. I can bring that 6 down and get the natural log of x. So now it's easy to differentiate dy dx. Leave the 6, and the log of x gives you 1 over x, and you're done. But it helped to use the power rule first. Okay, number 2, the natural log of the cube root of 4 minus x squared. Now for this one, I'm going to use some algebraic techniques to simplify this first. Oh, I forgot my y. Okay, so now I'm going to write y is equal to the natural log. This becomes 4 minus x squared. And since it's a cube root, then that becomes to the 1/3 power. Okay, so that makes it much easier to work with now, because now I can use my power rule and make this y is equal to 1/3 the natural log of 4 minus x squared. So now that I have that, I can do my dy dx. The 1/3 stays out there. The 4 minus x squared goes in the denominator. And then I need to multiply it by negative 2x. So my answer becomes negative 2x divided by 3 times 4 minus x squared. Okay. Guess who's going to do number 3? You are. Okay. So I'll give you a few minutes to work out number 3 by yourself. Anybody think they're done?
Can you scroll back up to the formula, please?
The formula. Oh, here we go.
Yeah. Thank you. I got it. Thank you.
Okay. Anyone have an answer for me?
I have an answer.
Okay, Lawrence.
I got 3 times 4 minus cosine x over 4x minus sine x.
That's correct. Okay, so we simplified this and made this y is equal to 3 times the natural log of 4x minus sine x. Okay. So then we said dy dx. We have a 3. Then 4x minus sine x goes in the denominator. And 4 minus cosine x is in the numerator. And that's it. Okay. Number 4 is a little bit nastier. Okay, number 4. All right, so number 4 is a little bit thicker, so I'm going to talk you through number 4. But we're going to need to use the product rule and the power rule. So the first thing I'm going to do is say that y is equal to the natural log of 3x to the 5th minus 3 squared plus the natural log of the sine of x squared. That's the sine squared of x, is the sine of x squared. Okay, so although it looked bad, now it's not too bad because now we're going to get 2 times the natural log of 3x to the 5th minus 3 plus 2 times the natural log of the sine of x. So now when I do dy dx, I get 2, then this 3x squared, 3x to the 5th minus 3 goes in the denominator, and I get 15x to the 4th in the numerator, plus 2 times, I'm going to get the sine of x in the denominator and the cosine of x in the numerator. So that gives me dy dx is equal to 30x to the 4th. Oh, I think I divided by 3. That's what I did. There was 30, I divided by 3, so I got 10x to the 4th. And I got rid of the 3's, so I just had, whoa. Okay, you want to be like that? X to the 5th minus 3 plus 2 times the cotangent of x. Okay, and that's our answer. Okay, any questions about that? Basically, taking derivatives of logarithmic functions is going to require the use of the product rule, the quotient rule, and the power rule for simplification. Okay. All righty. So now suppose you have something like y is equal to x to the 2x, and you need to find dy dx. Well, we can't use our power rule because you know where we have y is equal to x to the 2x. Our power rule, which is derivative with respect to x of x to the n equaling nx to the n minus 1, that doesn't work. So we can't go like, we can't do that. That's broken. Nope, can't do it. All right, so since we can't do that, we have to find another way to take the derivative of x to the 2x. That's a really big function. Okay. That function grows enormously, but we want to still take the derivative of it. So in order to do those kinds of little crazy problems, we're going to use logarithmic differentiation. Okay, so for logarithmic differentiation, you'll know you need to use it when the thing that you want to take the derivative of looks like x to a power of x or something crazy, or you have something that's just, you want to take the derivative of it and it's just like full of terms. And so we need to simplify it. So the method is to start with y is equal to f of x. You're going to take the log of both sides. So you're going to get the log of y is the log of f of x. Then I want to take the derivative of both sides. So when I take the derivative of the left side, the derivative of y is going to, log y is going to give me 1 over y. But remember, y is a function of x, so I have to use the chain rule to get dy dx. And on the right-hand side, I'm just taking the derivative with respect to x of whatever I got. But after I do that, then all I need to do is just multiply by y, because I'm trying to solve for dy dx. So therefore, I get dy dx is equal to y times the derivative with respect to x of whatever we found on the left hand, on the right hand side. Okay. Okay. So I have two examples. All right, so that first example is a doozy. As you can see, you have a squared, you got a fourth root, you got a cube. It's like a lot going on there. Okay, so let's try to solve this. Okay, we want to take the derivative of this function. Okay. So the first thing I want to do is I'm going to write it in a form that makes sense to me. So I'm going to write y is equal to the cosine of x squared. I can work with that. And in the denominator, I have 2x to the 5th plus 1. And what's the exponent going to be?
Three-fourths.
3/4. Somebody knows their algebra. Okay, so now that it is something I can work with, now I want to plow through and take the log. So I'm going to take the log of y, it's the left-hand side, and the log of this mess, which is cosine of x squared divided by 2x to the 5th plus 1 to the 3/4 power. Okay, so now I can simplify the right-hand side. Anybody want to help me? I have the log of y on the left-hand side. Remember, there's still no derivatives. We're only simplifying it. The only thing we did was take the log of both sides. So I need to simplify.
So you do the quotient rule?
Yes. Can you tell me how to do the log with the quotient?
So it'd be what, ln cosine x squared
Okay.
minus,
Minus. Keep
Oh,
going,
minus-
you're good.
oh, minus 2x to the 5th plus 1 to the 3/4.
Okay, how's that looking for you? Now what can you do?
I'll get the y and the u.
Okay, we're going to take the derivative. That's exactly right. But we still need to simplify one more step. We want
Can
to
you use the power
So
rule?
that
Okay.
3/4,
go ahead.
you bring the 2 in front, 2 ln cosine x minus 3/4 ln.
Okay. So now I'm going to take the derivative 1 over y dy dx is equal to, now take the derivative. Hello?
Oh.
Yes.
The derivative, so it'd be 2 times.
Wouldn't good.
We actually did this exact same problem with the derivative of the log of the cosine of x. We did this one already.
Would it be negative 2 10x?
Negative 2 what?
10x.
Tangent x. Okay.
See, put that on top. So that would be 3x over 2x squared plus 1.
Okay, a little bit more than that, but good. 3 over 4. We still have 3 over 4. And then we have 2x squared plus 1. Somehow that became 2x squared and it was 2x to the 5th. And so therefore its derivative is 10x to the 4th. Okay, so now we're good. Because now it says dy dx says multiply by the original y that you had and make it times this. So this is negative 2 tangent x minus divide by 2. So I think I get 15x to the 4th over 2 times 2x to the 5th plus 1. (30 over 8). Divide everything by, take a 2 out of there, take a 2 out of there, that leaves 15. 15 out of 2. That don't seem right. I have 30, oh, because I have 30 over 4. Okay. This is in parentheses. All right, so that is correct. So now I just need to multiply. So I get dy dx.
Wouldn't it be two for the denominator 2 times 2x to the 5th power plus 2?
It is, but I'm not going to multiply it out. Remember I told you about multiplying stuff out? Just leave it
Okay.
factored.
Okay.
Okay. So y, I don't remember y. This might not be the right y. Yes, it is. That is the right y. So it's going to take that y, and then it's going to multiply it by minus 2 tangent of x. Thing scared me. Minus 15 x to the 4th over 2 times 2x to the 5th plus 1. And we get that whole thing. Okay.
Actually, I
Yeah.
think that one, I think that should be a 2.
We think the 1 should be a 2.
Yes.
I'm trying to think, what 1 are you talking about?
The one inside the denominator, like in that parentheses.
I thought you said don't multiply it.
Yeah, I'm not.
Yeah, but even without multiplying, like earlier when you did 3/4 times 10x to the all that stuff, when you
That would be 30 over 4, right? 3
uh,
times 10 is 30 over
then
4.
multiply the 4 by the 2x 5th plus 1.
Oh, I didn't multiply it. I said this becomes 15 over 2.
How?
30 over 4. So look right here. 3 times 10 divided by 4 is 30 over 4. This 3 times 10 over 4 is 30 over 4. That's the same as 15 over 2.
Okay.
Yes,
Yeah.
but then I'm going to leave the 2 where it is. It's still 15 over 2. So I haven't factored that 2 in at all. That's it.
Okay.
Okay, are we good?
Yes.
All right. Okay, let's see where we are in the notes. Okay, so we are at recall. Good. Okay. So we're going to start to introduce the exponential. So let's recall what we've been looking at today. We've been looking at this function called the logarithm function. And the logarithm function, which we already know, is defined as the log of x is equal to the integral from 1 to x of 1 over t dt. So that's how we define the log function, and we graphed it, okay? So you can actually plot it. All right, so now there's only one number and one number only, such that the log of that number is actually equal to 1. All right, so that means the log of that number is actually equal to 1, and that number is e. E happens to be 2.71-828-1828-459045 and some digits, okay? So that number is E. So what does that mean? That means there's only one number all right, where if I plot 1 over x, and then I did the log function, here's 1. And so here's 1, and here's e somewhere. That is the only number where we can actually do this, and the integral will be 1. So it says the area under the curve of the function 1 over x, 1 over t dt, can only be 1 when x is e. All right, so e is a special number. All right, and so when we talk about e, we can get what we call this exponential function that looks like e to the x. So what is that? So for the number e that's fixed, we get this. I think I already drew it. Yeah, I drew that. I'm trying to think, was there something else I wanted to do it with? No, I think that was it. Okay, let me take a quick peek at my notes. I did logarithmic differentiation. Okay, I'm here. Okay, this is where I am. All right, so the exponential function is the function f of x equals e to the x. All right, and so the exponential function looks as such. So here, here is the logarithm function. Well, yeah, the logarithm function we said looked like this. 1, 2, 3, 4. And the exponential function looks like this. And by golly, they are inverse functions of each other. So right along the line y equals x, you can see the symmetry of the two functions. All right, this one being y equal to the natural log of x, and this one being y equal to e to the x. Okay, I'm going to stop there.